All right, let's start off this unit on circular motion with talking about the law of universal gravitation. So, before we get to Newton's study on gravity, it's kind of important to understand where astronomy was when Newton came onto the scene. So, you had two major figures. You had Tycho Brahe and you had Johannes Kepler. And Tycho Brahe was this Danish nobleman who collected tons of astronomical data on this island observatory that he built. He was one of the richest people in Denmark, right below the king, basically. And what he did is he would spend his nights collecting data and compiling massive amounts of planetary information. Basically, it was the biggest collection of astronomical data present in the world for the most part. But the thing is, he never actually did anything with it. So eventually, he dies. Johannes Kepler is his assistant. His assistant takes all the data, books it back to Germany, and he comes up with Kepler's three laws, which we'll cover at the end of circular motion here. But the reason we mention them is because, yes, Kepler's laws describe exactly how the planets behave in terms of orbits, but they don't explain why. Kepler never got into the actual why of why the planets do that. And so that's where Newton comes onto the scene, and Newton hates not knowing why. Right? He's the guy who he wanted to know whether color was something out here in the world or in here in your brain, right? So he took a needle and stuck it right behind his eye, right near the bridge of the nose, and just started to poke on the back of his eyeball to see if he could force himself to see colors. Right? That's how dedicated Newton is to wanting to know the why of nature. Right? So he's not content with Kepler's laws just describing perfectly how the planets orbit. He wants to know why exactly they orbit. And so that's when we get into that, famous story, right, where according to legend, Newton is walking through an orchard and an apple falls down, hits him on the head, right? And he looks at the apple and he says to himself, "Well, I know why this apple fell, right? Galileo has been around. Galileo proved that the acceleration due to gravity on Earth was 9.8 meters per second squared." But then the second part of that legend that always gets forgotten is he looks up at the moon and he asks himself, "Okay, is the moon also falling?" Right? We know this apple falls because of gravity. Is the moon falling? And so that's where we get to Newton performing a thought experiment. Now, if you continue into AP Physics 2, what you'll see is a lot of times thought experiments are done by famous physicists like Einstein or Newton when you lack the ability to perform an experiment. And what a thought experiment is basically just using logic to think about what would logically occur if X happened. So what Newton did is he imagined himself to have a mountain. And on top of that mountain, he's got himself a cannon. And that cannon is going to fire off cannonballs horizontally. And so in his mind, he pictures, okay, what's going to happen? Well, I fire that cannon with X velocity, right? And what's going to happen? Well, the cannonball is going to come crashing down to Earth. If I fire it with more speed, it's going to go a little further and then crash down to Earth. If I increase the speed, it's going to go a little further, crash down to Earth. Well, what he started to think about was at some point, there is some velocity at which you can fire that cannonball where the drop in altitude of that cannonball will match the curvature of the Earth. And in that case, well, the cannonball never comes down, right? Because for every, say, 1 meter that it drops in altitude, the Earth's curved by 1 meter. And so what he reckons is that the moon is just like that cannonball, where yes, it's under the influence of gravity, it's in a state of free fall, but the reason it never comes down to Earth is because it's got this proper speed. And that's why it has a circular orbit. So after he concludes that the moon is, in fact, in a state of free fall, like that apple falling from the apple tree in the orchard, he starts to examine what was known about gravity and about planetary motion at the time. So, thanks to Galileo, he knew that on the surface of the Earth, the apple falls at 9.8 meters per second squared. Thanks to Kepler's data, he knew that the Moon had an acceleration around the Earth of 0.00272 meters per second squared. And so, what he started to think about was, well, what's the big difference between the apple and the Moon? Well, the distance from the center of the Earth. And so, what he started to look at was that distance. And what he found was that the distance that the Moon is compared to the apple from the center of the Earth is 60 times further. Right? And so what he figured out is, well, okay, the moon is 60 times further from the center of the Earth than the apple on the apple tree is. And also, if you look at the ratio of the acceleration of the moon versus the acceleration of the apple due to gravity, there's a 1 to 3600 ratio. Right? And so 60 squared is 3600. So what he comes up with is that gravity must obey an inverse square law, meaning that the distance from the center of the Earth is going to determine how strong that force of gravity acting on an object is. Right? So the further away you get, the lesser the force of gravity is. And so all he manages to do is come up with a proportion, though. Right? And that proportion is that the force of gravity is proportional to 1 over the distance from the center of the Earth squared. Now, the big thing, though, with Newton and gravity is the statement he made that gravitation is universal. And when we talk about universal, we're not talking about, space and the universe. We're talking about universal as in applying to all things. So, Newton's law of universal gravitation states that all objects have a force of gravitation with every other object. So, there is a force of gravity between me and the pencil sitting on my desk. Well, why doesn't that pencil get up and start orbiting me? Well, because from a big picture perspective, our masses are insignificant, right? Mass is going to play a huge part in the force of gravity. But again, the big thing is that everything is gravitationally attracted to everything else. Now, that's kind of where we stop for a while, and it takes about 100 years for us to make any more progress on determining a formula for gravitation. And so eventually in 1798, you get Lord Henry Cavendish. He performs this experiment involving two little spheres that are slightly, moving due to the gravitational force between them, and it's a incredibly tedious experiment. But he manages to find what we call the universal gravitation constant. And that universal gravitation constant, big G, is 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared. So it's a very, very, very small number, right? And so that constant being a very tiny number indicates how weak the force of gravity truly is. Right? And so that brings us to an actual equation for determining the force of gravity. Now, the force of gravity is going to be dependent on that universal gravitation constant, the two masses involved, and the distance squared between those two masses. Now, keep in mind, you've got to keep your masses in kilograms, and you've got to keep your distance between the two objects in meters. Now, often we're going to be dealing with things that are super far apart, so you're going to be given things in kilometers. Make sure that you're converting those to meters. So let's take a look at example problem 1. We want to determine the force of gravitational attraction between the Earth, which has a mass of 5.98 times 10 to the 24th kilograms, and a 70 kilogram physics student if the student is standing at sea level, a distance of 6.38 times 10 to the 6 meters from Earth's center. Alright, so let's start with force of gravity is equal to constant times your two masses over r squared. So the force of gravity in this case is equal to your constant times the mass of the Earth, so 5.98 times 10 to the 24th kilograms, times 70 kilograms student, and all that over 6.38 times 10 to the 6 meters squared. So the force of gravity in this case comes out to 686.2 newtons. Right, so the student on the surface at sea level weighs 686.2 newtons. Now, in example problem 2, we're putting the kid on an airplane, and now he is 6.39 times 10 to the 6 meters. So all the same givens as far as the two masses are concerned. We're just altering the distance a little bit there. So take a second and calculate that out and see if there's a difference between the weight of the student at sea level versus the weight of the student on an airplane. And you should get a new weight for the student of 684.1 newtons. So as you move away from the center of the Earth, right, your actual weight, the force of gravity acting upon your mass, decreases. Right, so technically you weigh a little bit less when you're on a flight than you do when you are landed. Now, we can also derive a secondary formula that will allow us to find the gravitational acceleration on any given planet. Now, if we look at our gravitation formula, right, we have force of gravity is equal to G times your two masses over R squared. Now, think about how we used to calculate weight. Now, I'm going to call these two masses something different. I'm going to call this mass of the object, so MO, and I'm going to call this mass of the planet, so MP, right? Because these are the two masses that are interacting with each other when we're dealing with an object at the surface level of a planet. Now, when we were finding the weight of an object earlier, right, we always took the mass of the object times the acceleration due to gravity. So that equals G times the mass of the object times the mass of the planet over the planet's radius squared. Right, because if we're talking about an object at surface level on a planet, the R there, the distance between those two objects, would be the actual radius of the planet itself. Now, we got mass of the object on both sides. That cancels. And so what we're left with is, if we want to know the acceleration due to gravity on any given planet, it's equal to that constant times the mass of the planet itself over the radius of the planet squared. Right, so we can easily determine the acceleration due to gravity on any planet as long as we know the planet's mass and as long as we know the planet's radius. So in example problem 3, we got Mars. It's got a mass of 6.4169 times 10 to the 23rd kilograms and a radius of 3.397 times 10 to the 6 meters. And we want to know the acceleration due to gravity on the surface of Mars. Well, if we want to know the acceleration due to gravity, we've got our constant, times the mass, which is 6.4169 times 10 to the 23rd, and all of that over the radius of the planet, which is 3.397 times 10 to the 3rd, 10 to the 6th squared. So we get an acceleration due to gravity on Mars of 3.71 meters per second squared. Oops. And so that's useful to be able to calculate the acceleration due to gravity on any given planet. I mean, think about what we just did on Mars, right? We landed that second rover, the Perseverance. Without knowing the acceleration due to gravity on the surface of Mars, well, it would be extremely unlikely that you'd be able to land, any sort of exploratory device there. So I'm going to post a basic set of these. The law of universal gravitation is pretty straightforward. And then the next lecture, we will start covering uniform circular motion. All right, have a good one. I will see you all soon.